Hello, my name is Aziz Niyazov, and I would like to present you our work, User-Driven Constraints for Layout Optimization in Augmented Reality. This work is done at University of Toulouse-3 in France in collaboration with Monash University in Australia. Most of you saw the movie Iron Man, where Tony Stark easily interacts with holograms. Without any effort, he places virtual content here and there, just using hand gestures and his voice assistant. But in real life, current commercial devices are still far from what we see in the movies. Yet, current technologies can track the environment, produce good quality holograms, and recognize gestures. Recent studies have found that displaying virtual data in 2D or 3D around the user and in the real world can help them understand space better, reduce information overload, and allow for more natural ways of interaction, such as gestural input and body-based navigation. Although there is a lot of potential for using virtual content in our surroundings, there is a limitation of how we interact with it. Specifically, it's tedious and time-consuming to arrange the content manually, yet critical for an efficient data access. Previous work have tried to overcome this challenge. They introduced multiple approaches to automatically optimize the content placement in augmented reality environments, removing the need for any user input. For example, in Snap to Reality, the authors used the geometry of the environment and extracted the edges and surfaces to snap virtual objects to them. The other optimization approaches explored the use of spatial consistency, user perspective, usage frequency, or semantics. However, these approaches are limited in two aspects. First, most of these approaches lack any form of user control over the resulting placement optimization. Second, for the most part, these constraints have been designed and tested in isolation from each other, leaving aside the question of how to allow the user to define several constraints in a fluid and natural way. We thus lack a holistic approach that unifies multiple constraints and the input interaction, which bring interactivity into augmented reality layout optimization. We address the question of how to bring interactivity into layout optimization systems through a use case scenario. This is a researcher, John. His workspace consists of a combination of physical and virtual objects. Physical objects include a desk, laptop, mouse, as well as decorative elements and surrounding walls. Virtual objects exist in augmented reality and consist of virtual nodes, virtual documents, as well as virtual tools and widgets. John uses the user-driven constraint layout optimization tool to easily arrange the virtual objects. First, he wants the nodes scattered on the wall to be aligned near the corner. However, he doesn't want these nodes to cover his Best Paper Award certificate. To achieve this layout, he first created an exclusion surface covering the certificate, followed by an attractive edge along the corner of the wall. The edge causes the nodes to move towards the corner, while the exclusion surface prevents nodes from covering the certificate. Next, he would prefer to see his non-work-related to-do list on the surface in front of him, but only after closing the laptop lid to prevent being disturbed by the work-unrelated activities. To achieve this occlusion-aware layout, he creates an in-view surface right behind the laptop. When John next opens his laptop lid, hiding the surface region from view, any nodes placed there will be automatically moved elsewhere. Moreover, John likes listening to the music, and he wanted to have easy access to a music player. He created another attractive edge on the edge of the desk. This time, he defines a semantic attractive edge that only attracts a specific type of content, which he assigns to a music player. There are cases when it may be useful for John to define a preference for multiple containment surfaces. A containment surface is a user-defined 2D region that attracts virtual content. For example, John knows he will need quick access to an email list and notes. For this, he creates a high-priority containment surface near his mousepad. John also wants to have an additional surface on which he can situate virtual research paper downloaded from the internet. For this, he creates a low-priority containment surface on the left side of the table. The two containment surfaces now have different priorities assigned. After the research paper is downloaded, it will be positioned on the low-priority surface, because the high-priority surface reached its full capacity. We also envisage how our user-driven constraints approach helps in collaborative scenarios, in particular preparing a shared workspace before collaborative activities take place. John has scheduled a quick meeting with his colleague Sarah. He knows from experience that he will be sitting in his chair, while Sarah will be standing next to him. In this case, John and Sarah will have different user perspective of their environment, and defining surfaces on which they can place virtual content beforehand can help avoid confusion caused by occlusions. Before the meeting, John creates a camera frustum for his own expected perspective and a second one for Sarah's expected perspective. The intersection of two surfaces then becomes the shared containment surface. Based on this user scenario and recommendations from previous works, we present our user-driven constraints. Our approach allows users to refine virtual content placement optimization unifies the interaction experience by considering all the constraints at once, adopts a deviceless approach based on hand gestures, supports direct manipulation, and avoids GUIs that break the interaction flow. In this work, we create a design space of interactive layout optimization for augmented reality environments. We conduct a user elicitation study exploring which gestures would user perform to conduct such interactive optimizations. We design and implement an interactive prototype demonstrating our approach. And finally, we validate our approach through a controlled summative study. Given the limited amount of time, I will present the summary of gesture elicitation and summative studies. Regarding the gestures, we can summarize our result as follows. Collected gesture set was made of various simple gestures rather than more complex. The selection of the regions was almost always performed using raycasting. Many gestures started with the raycasting gesture were followed by a specific simple but meaningful gesture to define the appropriate constraint, for example, a containment. The interaction follows object action model, where the user first selects the object, which is the surface in this case, and then applies an action, which is a user-driven constraint. The summative study allowed us to collect first feedback on our gestures and on the interest of our approach. Overall, gestures were appreciated and found easy to perform. Our user-driven approach was preferred to manual arrangement and requires lower temporal and physical demands. Besides, the study allowed us to test the use of several constraints at the same time. Our research revealed some criteria that people tend to apply when defining hand gesture for user-driven constraints. First, participants tried to reduce complexity of interaction by using simple gestures. For example, if the attractive edge was created by dragging inwards, the repulsive edge was created by dragging outwards. Second, the participant wanted the interaction to be consistent when creating regions and constraints. For instance, the semantic label was added using the same gesture for all types of regions. Moreover, our research validates our initial design objectives. For example, participants felt a similar level of control with our approach as with the manual interaction. This validates human-in-the-loop objectives. People were able to use various hand gestures to configure their layout without any explicit gesture delimiter. This validates holistic design and natural hand gesture objectives. Creating a containment surface with a direct hand ray was intuitive, as well as the bimanual gesture to create an edge. Also, participants were able to define a complex spatial layout while using no menus. As a future work, we consider to provide clear feedback and instructions for gestures. For instance, highlighting the area where the gesture is applied before pinch is released. Another future challenge will be to define the direction of attraction, while limiting gesture delimiters and using no GUIs. Next, future work would be to extend the current virtual content to other types of UI, such as 3D virtual objects or large windows. Moreover, we only consider a gesture that can be performed on HoloLens 2, but our study revealed that participants would like to perform gestures that are not recognized by the device. Also, developing a more robust optimization system will require to use an external solver, which has been successfully used for optimizing the placement of 2D widgets on projected interfaces. Not to mention, future work may address the non-trivial challenge of extending this 2D optimization to 3D, or predicting the impact on user performance. Thank you very much for your attention. Feel free to ask questions.